In this video, we're going to talk about how do I find the area underneath of a surface. This multivariable calculus problem is completely analogous to a single variable problem that we answered back in first year calculus, which was the area underneath of a curve. And the idea back when we talked about the area underneath of a curve was that we would take the region and we would break it up into a bunch of different rectangles. And when we broke the region into a bunch of different rectangles, the area of each of those rectangles was easy to compute, and then we could add up all of the areas of those rectangles, and that would give us an approximation for the area under the curve of a single variable function. The situation in multivariable calculus is exactly the same, except instead of little rectangles, I'm adding up little boxes. And then in both of these two different stories, I could get a better and better approximation by taking a larger and larger number of individual subdivisions. For instance, I could have this larger number of rectangles here, a larger number of little boxes, and I could do it once again. And the more I take my domain and divide it up into an increasingly large number of increasingly small little rectangles, then I'm going to get a better and better approximation of my curve. Let me zoom in on one particular little box here. Notice that at some points in the box, this box is higher than the graph of the function, and at other points, the graph of the function is higher. And so what we have is a little error appearing, namely that as it sticks its way out above the surface, you're adding up too much, and when it's beneath the surface, you're adding up a little bit too little. But as you increase the number of them, as the size of these get smaller, the argument is that these errors, by approximating in this way, are going to get smaller and smaller and smaller. Let's see how we can define this a bit more formally. I'm going to focus in just on the domain, and I've specified some rectangle in the domain. This rectangle has a width that I will define to be delta x, and it has a height change, a delta y, and I'll define that to be the delta y. I'm imagining that there's going to be a large number of these little rectangles subdividing up the domain. And so I actually call it delta xk and delta yk to denote that I'm talking about the kth such little rectangle in the division of my domain. And then the next thing I want to do is I need to figure out what the height of the box is above this little rectangle. And to do that, I'm going to plug it into my function, but plug what into my function? This is a whole little region. I need to choose a specific point that I will plug into my function. So let me choose a pair xk, yk, and the pair xk, yk is just some point anywhere inside of my rectangle. It doesn't matter. You and I can make different choices as to where that point's going to be, and well, for our approximation, our choices might matter. In the limit, as you go towards an infinitely large number of infinitesimally small number of these little subdivisions, where exactly you choose the xk, yk inside of the rectangle is not going to actually matter. So that's the domain. Now if I go back and look at what it looks like for the graph of the function, down the base I have that delta xk and delta yk. And then if I take that specified point, the xk, yk, if I take f of that point is going to give me the height of my particular box. And so the volume of this box is going to be, well, base times height. So it's the product of the delta xk and delta yk in the base, and then multiplied by the height, which is the function value at xk, yk. So the basic idea I'm going to do is I'm going to compute that volume for this one particular box, and then I'm going to add it up over all of them, and finally I'm going to take a limit in some sense. Now, let's see how we do this more properly. So the first thing I'm going to do, if you give me a region, and by the way, for this video, the region has to be a rectangular region, a region where it's just a change in x and a change in y. But if you have such a region, then the first thing that I'm going to do is I'm going to break it up. I'm going to partition it into a bunch of small little rectangles. And the area of each of those rectangles is going to be given by the product of the change in xk times the change in yk. So the total little area that I have is this product of these two things. Then, if I take this rectangular region, which is broken up into a whole bunch of little rectangles, in each rectangle, I'm going to choose some particular point. So I'm going to choose an xk, yk inside of each of my little rectangles. Then, if I want to approximate the volumes, this is not exactly the answer, but if I'm going to do an approximation, if my partition of that big rectangular region into n different small little rectangles, then I will take the sum. That's what this notation means. Sigma is the sum from 1 up to n, and I'm adding up the sum of all the volumes of these little boxes, where the heights are given by the f of xk, yk, and where the widths are given by the delta xk, delta yk. And then comes the real magic of Riemann integration. This volume is an approximation. But what I'm going to do is I am going to define the volume under this region by talking about a particular limit. I'm going to define the volume to be equal to a limit as the length of p goes to 0, we'll talk about that, of this sum from 1 up to n of all of these little volumes, the f of xk, yk times the delta xk, delta yk. And then what is the limit doing? Well, P is just the name I give for this partition where I took this big region and I partitioned it into the sum of a bunch of little small rectangles. And when I take that the length of P goes to 0, what I just mean by that is that the largest rectangle in that partition, some might be bigger, some might be smaller, I'm saying the largest rectangle is going to go to 0 area, which means all the other rectangles are going to go to 0 as well. And indeed, if the area of these rectangles is going to 0, what we're meaning is that the number of those rectangles is going to infinity. So there's many different ways to talk about this limit, which means I'm getting a better and better cutting up of my region into a finer and finer partition where the maximum size of any individual AK is going to 0 and the number of them is going to infinity. Nevertheless, I take that limit that I'm trying to describe, I take that limit for this particular sum, and that's going to be my definition of volume. Let's see an example. The first thing I want to do is consider the same function that I've been talking about, 9 minus x squared minus y squared, and on the same region that I plotted here. So the x is between minus 2 and 2, and the y is between minus 2 and 2. The way I represent this is using one interval times another interval. That's my notation for talking about a region that bounds the x and the y. So the x between minus 2 and 2, and the y between minus 2 and 2. Then the next thing I'm going to do is I'm going to go and approximate this by just 4 rectangles. And the reason I'm choosing only 4 rectangles is I want it to be something that we actually can compute out of this video, not 18 or any other number. But for 4, I think we can compute it. So what you see in the graphic here is these 4 different boxes, each of different heights. And my approximate volume is going to be the sum of the volumes of those 4 boxes. If I focus in on the domain, then what I'm going to have is these 4 little rectangles, an A1, an A2, an A3, and an A4. And I'm going to make a specific choice. I'm going to choose the xk, yk to be on the bottom left corner of these 4 different boxes. So in other words, for the A1, the specific choice that I'm going to put down here is the point minus 2, 2. And then for the A2, the A3, and the A4, I can just put these other 4 points always at the bottom left corner. Could have chosen the top right corner, could have chosen any corner, but for this approximation, that's the corner I'm going to choose. Now I'm going to step away because there's going to be a bunch of formulas on the screen. Then what I want to do is I'm going to say my volume is approximately equal to the sum of 4 things, these 4 different boxes, these 4 different rectangles with heights above them, and that those heights are going to be given by the function value at the 4 points that I've chosen, multiplied by the delta xk, delta yk. Well, in this example, the change in the x and the change in the y for any of those 4 little rectangles is just 2. So this is nothing but the sum of the function values times 4 times 2 squared. I'm going to evaluate this function at the 4 different points. So I'll evaluate the function at minus 2, 0, minus 2, minus 2, 0, 0, 0. Those are the 4 different points, and each of them gets multiplied by this 2 squared. If I just plug those into the function, I get 1 plus 5 plus 5 plus 9 multiplied by 2 squared, and that's going to give me a value of 80. So this is an approximation to the area under this particular surface.